Okay, so we've been taking a look at this system, which we proved was Hamiltonian. We actually found our Hamiltonian function was h of xy equals sine xy, so that I know that the level curves for this are going to be the solutions to this system. Okay, that's pretty cool. What I want to do before I draw the phase portrait for this system is I want to just take a look in general at the types of equilibrium solutions that we can have if we have a Hamiltonian system. And that's because I know that J, my Jacobian matrix, is just the partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, partial of g with respect to y. But because f and g already have this relationship of being partial derivatives of the function h, my Hamiltonian function, that gives this a sort of interesting structure. Because each of these partials of f and g are actually going to be second partials of my Hamiltonian function. So if I take the partial of f with respect to x, I'm getting the partial with respect to x of the partial of h with respect to y. So I'm getting a mixed partial of h. If I take the partial with respect to y, I'm getting the partial with respect to y of the partial of h with respect to y. So I'm getting one of my non-mixed second partials. Okay, so here, if I'm taking the partials of g, I'm going to get here the partial of, with respect to x, of the opposite of the partial of h with respect to x. So I'm going to be getting the opposite of the non-mixed partial, second partial with respect to x. And then here, I'm going to be taking the partial with respect to y of the opposite of the partial of h with respect to x. So I'm getting the opposite of the other mixed second partial. But what that means is that this number and this number are always going to be opposites of each other, because one is this mixed second partial, the other is the opposite of the mixed second partial. So I'm going to just indicate that by saying I'm going to have A, B, C, negative A. Okay. So B and C are obviously going to vary, and the value of A will vary, but whatever I have here, I'm going to always have the opposite of that there. Now what that means is that my trace is going to be 0, because the trace is just the sum of A plus negative A. Now the determinant is negative A squared minus BC. Okay. But that changes my characteristic equation, having that trace be 0, because in general I get lambda squared minus the trace times lambda. That term is going to drop out, plus the determinant. So I'm going to get plus the opposite of A squared minus BC is equal to 0. And so that's going to mean that lambda squared is A squared plus BC, where A, B, and C are just the entries of this matrix. They might be positive numbers, they might be negative numbers, but lambda is going to be plus or minus the square root of A squared plus BC. So I have just this. There's nothing in front of the plus or minus. And so that really gives me 3 possibilities for what I could have depending on the sign of this A squared plus BC. Okay. So it could be positive, it could be negative, and it could be 0. And then I can try to classify the equilibrium point. Okay. Now, if this is positive, this is just a real number. I'm getting positive that and negative that. So I'm going to have one positive eigenvalue, one negative eigenvalue. I know that's a saddle. And in that case, that works. The linear system has a saddle. I know that the nonlinear system also has a saddle. That's a time when linearization works. Okay. If this is a negative number, then this is a purely imaginary number. So I'm getting purely imaginary eigenvalues. So that means they're complex eigenvalues with 0 as the real part. So that would mean that I would have a center. Now, generally speaking, when I have a center, that would be a time when linearization fails. Because if the linear system has a center, it's entirely possible that the nonlinear system actually has a spiral source or a spiral sink. However, with a Hamiltonian system, I know that my solutions have to be level curves for a function, and I'm not going to be getting spirals for that. So this would be a center for both the linear and the nonlinear system. So the linear system that's approximating my Hamiltonian system would have a center. The Hamiltonian system would also have a center. As a general rule, if I've got a system and it's not linear and I use linearization and I get a center, that's not enough for me to classify the equilibrium point in my non-equilibrium solution. It's enough for me to narrow it down to it being one of 3 things: a center, a spiral source, or a spiral sink. If it's Hamiltonian, it's not a spiral source or a spiral sink, so it's got to be a center. Okay. Now the other possibility is that this could be 0 under here. Now, if that's the case, then 0 is the only eigenvalue I have. And when I have 0 as an eigenvalue, we simply can't classify the equilibrium solutions, even in the linear system. So we can't classify. But that's kind of interesting. That tells us that we're never going to have a source or a sink, not even a spiral source or a spiral sink. If it's a Hamiltonian system, I could have a saddle, I can have a center, I could have one of these things that I can't really classify that corresponds with 0 eigenvalues, but I will not have a sink or a source. Okay? And that's simply because if I'm looking at level curves for some function, they don't all approach one point or go away from one point. I can't have that behavior with level curves for a function of 2 variables. Okay, kind of cool. So I do want to draw the phase portrait for this. I think, though, let's make that be our next video, so we'll pick up with that next time around.